Who don't know me, my name is Kelly Frieda, and I am the chair of the Mass Envirothon Steering Committee. The Envirothon is Massachusetts' leading natural resource education program for high school students, emphasizing hands-on, team-oriented problem solving and community involvement that prepares young people for environmental careers and active citizenship. Even though this is not the way we or anyone wanted the year to go, we're glad to have you here this afternoon so we can keep learning together even though we're apart. Our presenter today is Bill Moulton, a civil engineer with the Department of Conservation and Recreation, Division of Water Supply Protection at the Wachusett Reservoir. Bill holds a BA in biology, BS of forestry, MS in environmental engineering, and has been employed by the Commonwealth since 1985. He has held positions as a laborer and a forester at the Blue Hills Reservation until 2005, when he became an environmental analyst at Wachusett Reservoir. He has been the regional engineer since 2008. When he is not working at Wachusett, Bill serves as vice chair of the Ashland Conservation Commission and is a past chair. He is also the parent of an Envirothon alumni, is a former Envirothon coach, and has served as a judge. On behalf of the Mass Envirothon Steering Committee, we would like to thank Bill for taking time out of his busy schedule to join us this afternoon. I want to encourage everyone to ask questions by using the Q&A button at the bottom of your screen. If you're on a cell phone, it's at the top. I would also like to remind everyone that this session is being recorded and will be available on the Mass Envirothon website at massenvirothon.org. Thank you and welcome, Bill.
All right, thank you. And I guess we'll start sharing screen. All right. So when Kelly came to me about this, sent me the flyer on this. So it was just water management and climate change, and they wanted me to focus sort of on gray and green infrastructure. So, you know, I have a little bit of a background in that, working at DCR, also in my role as on the Conservation Commission for my town. So let's keep moving forward. All right. So talking about Massachusetts, you know, water is an important component within Massachusetts, but some basics. We have a population of 6.9 million people. We have about 351 communities, that's towns and cities. Total land area is around 6.75 million acres, and total land acres is about 5 million acres. So go over an overview of the gray and green infrastructure. We'll start with stormwater, we'll move on to wastewater, then drinking water, flood control, and we'll talk about climate change. So what is infrastructure? Well, I mean, you see the slide right there, that's Wachusett Dam. That's infrastructure, but we'll give you some definitions. So Oxford Dictionary defines infrastructure as the basic physical and organizational structures and facilities, such as buildings, roads, power supplies needed for the operation of a society or enterprise. The Environmental Protection Agency defines infrastructure as the basic equipment and structures such as roads, bridges, buildings, water lines, and sewer systems that are essential for functional, healthy, and vibrant communities. So go to the gray infrastructure definition. So the Environmental Protection Agency defines it as traditional gray stormwater. It's designed to move urban stormwater away from built environment, and this includes curbs, gutters, drains, piping, and collection systems. The National Green Infrastructure Certification Program defines gray infrastructure refers to it as a constructed structures such as treatment facilities, sewer systems, stormwater systems, or storage basins. The term gray refers to the fact that such structures are often made of concrete. Green infrastructure definition. So the EPA, green stormwater infrastructure is designed to mimic nature and capture rainwater where it falls. Green infrastructure reduces and treats stormwater at its source while it's also providing multiple community benefits. So the National Green Infrastructure Certification Program defined it as the collection of engineered systems that utilize natural or green approaches to manage stormwater locally. Stormwater is stored temporarily at or near where it falls to be used by trees and vegetation, stored and used later for irrigation, or allowed to soak into the ground through the layers of soil, which remove pollutants from the stormwater through natural processes. So I actually found this in our state laws. So this is Mass General Law, Part 1, Title 2, Chapter 21, Section 26A. And that defined green infrastructure as practices involving the management of water, stormwater, wastewater to achieve water quality mandates set forth in the Federal Clean Water Act. Practices designed using natural or engineered techniques to capture, remove, or prevent nutrient, nitrogen, and phosphorus loading to any part of a water system, including groundwater deposits, discharges to stormwater from septic systems, wastewater treatment facilities, and stormwater runoff. So so that's our definitions for gray and green. But since a lot of that had to focus on stormwater, I thought I'd develop a more generic definition for our purpose. So gray infrastructure, simply put, is an engineered, hardened structures that convey, manage, or treat water. Green infrastructure, it's a more natural and less hardened engineered structures or systems that conserve and keep water locally to be managed and treated. Now, caveat is these definitions of terms can be relative to the subject, purpose, location, environment, and or scope. So which infrastructure do you think would be the best? Gray, that's probably your traditional infrastructure system. Green, that's your more natural system. We have both, would be a combination of the two systems. Now I've put in none. And what I mean by that is utilizing the natural ecosystem to manage the water. And then last would be all. So that would be use the system that best fits the situation. And that goes back to the definition or the caveat I had in the previous slide about the difference in the, relative to the subject, the purpose, location, environment, or scope. So I think you can't fit everything into one can. You've got to be able to tailor your infrastructure or your system to the needs and the situation, the environment. So what is stormwater? So stormwater will, rainwater comes down, it goes on roofs, it goes on lawns, driveways, walkways, streets, highways, parking lots, and they all, when that stormwater runs, it has to go somewhere. And so it as it travels across all these different surfaces, it picks up pollutants. a lot of material. So some of the common ones, you've got pesticides, so that includes both herbicides and insecticides, fertilizer, particularly nitrogen and phosphorus are the key, two key nutrients or biological waste from pets or from septic pathogens, trash. So you have plastic or paper or other debris. Vegetative waste, you have grass or leaves. Sediment, a lot of times we'll pick up soil and sand. De-icing agents, salt that's put down the roads. Metals, that can come from metal roofs or vehicles. Hydrocarbons, which will be oils and grease that comes off the vehicles. And then any other chemicals such as like paint or maybe mercury. So we'll start with stormwater gray infrastructure. So here's just a listing of the some gray infrastructure, roads and parking lots. I mean, I won't go over them, but they convey water. They are designed to shed water in a particular direction. And that's usually it goes to a catch basin. And then from catch basin goes into pipes. You also have drainage swales and channels that will take water. You have oil grit separators, proprietary separators, sediment forebays, and detention basins. So the picture here you have on the left is NARA headquarters. That's a drainage swale. It's rock lined. Sometimes you can have vegetated or concrete. And then it goes to a catch basin. You look further at the far end of the basin of the channel there, drainage channel. There's a drop inlet. That's a different type of structure, but it acts as similar to a catch basin. Then down below, you have a discharge pipe that comes from the left, and then that goes into a forebay. Forebay is designed to catch sediment. And you can see on the right here where there's a little bit of a berm. So it catches, the water comes in, has a chance to sort of slow down the velocity, and then it will move over the berm into the main part of your detention basin, which is right here. This structure right here is basically a drainage device, a structure for the basin. Unfortunately, you can't see you see the top, there's a grate there, so water will build up and flow into that and then out of the basin. But there's also, on the other side of this, there's a grate, and that's on the side of it, and that allows water flow through. The detention basin is not designed to really treat water. You might get a little bit because of the sediment it catches, but it's more designed to attenuate or sort of slow down stormwater flow. So it will reduce peak discharges, reduces our erosion potential. Another, go back to the detention of the catch basin. A lot of times in catch basins, you want to have what they call a deep sump catch basin. That means it's like at least 4 feet deep from where the pipe that takes it out of the basin. So it's 4 feet from that pipe down to the bottom of the basin. That allows it to be able to capture sediment. And then that pipe then goes to most likely another structure, but sometimes it will just discharge into a waterway or just out into the woods. So. This is an oil grit separator. It's designed to, it's designed to capture sediment such as sand, soil, and it's done through baffles. It's also designed to capture any oil that may, when you have a storm, it will pick up oils that are on the roadway. and bring them into it, and this will capture it so that oil is held there and it can be pumped out. And on the right, we have a proprietary separator. That is a system that uses similar. It's designed to remove sediment and oil from the stormwater, but it does it through hydrodynamic forces. It uses velocities to be able to trap the sediment. This structure is actually a storm scepter. That's one of the structures we have for our stormwater system. Another one you find will be what they call a downstream defender. So next we'll go over green infrastructure. So start with a water quality swale, rain gardens, bioretention area, a wet basin, like a structured wetland basin, infiltration basins, porous pavement, permeable pavers, rain barrels, and cisterns. And then just want to make a comment about low impact development. You'll see that a lot, especially related to green infrastructure. Green infrastructure utilizes, low impact development utilizes green infrastructure. So LED, low impact development, is a system and practices that use or mimic the natural process. That's a definition from the EPA. But this also, it's a sort of a process where you try to eliminate your stormwater runoff, and that can be done in a variety of ways. One way would be reducing the widths of your roadways. Many roadways would be, like out in my house, it's probably about 26 feet across, wide. You could probably reduce that to 22 and still have safe travel of traffic. It's just too wide. And actually, the wider it is, sometimes people tend to drive a little faster. So that would be another benefit by narrowing. So this is a bioretention area. That's one of our stormwater systems. What happens is it's designed so stormwater will flow into a storm into a forebay, and then it will come into the bioretention area. And this is designed to capture sediment. It's also designed to treat your runoff. It also infiltrates, so you're recharging the groundwater. It's designed to capture a particular storm event. Typically, this one is designed to capture a 100-year storm event. You may also see that referred to as a 1% event. And then we have, on the right here, we have a rain garden. So this rain garden was just put in this year. For a small parking area, generally they're smaller. They're not designed to take large areas. You can, generally they're designed to capture what they call first flush from a storm. So if you get a rainstorm, you get the first amount of stormwater that runs off, it will capture it and treat it. It will infiltrate. Those plants will take up some of the pollutants. So that's what, and it has this actually has, sometimes they have forebays, sometimes they don't. This one actually, you can see the stone there. That's a little bit of a forebay to capture any sediment that comes down from the swale and runs along the length of the parking area. And you'll see they're generally pretty small. They'll be put along roadsides just to capture the first flush. And as I said, that's where you get most of the pollutants are picked up from the roadway. And if you can treat that, you're providing better water quality going into your water sources. This is a wet detention basin or a wet basin. you'll see it maintains water in it all the time. It's designed to capture storm events of particularly a 100-year storm event or whatever it's designed to capture sediment and for pollutant removal. You look at the water quality swale here. This is designed to, they're usually vegetated, and sometimes they'll have check dams. And a check dam is just a bunch of stone that would be put across the width of the swale in order to sort of slow down the stormwater velocity in order to prevent scouring, plus also it allows you to capture sediment. So it's designed to capture sediment, some pollutant removal. Usually it's not designed to handle a large storm event. Usually it's a smaller storm event, like maybe a 2 or 10-year storm event. So typically, and this goes to wetland, the Wetlands Protection Act is when a system is designed, they look at it within a 2, 10, 25, and 100-year storm. And a lot of systems are designed for a 100-year storm, but also they tend to be a lot larger. So based on the situation, they may run for a 10-year event in order to capture some sediment and pollutant removal. So here are the infiltration basins. So you have 2 types of infiltration basins. You have it above ground. So on the left here, you have stormwater that runs off the roadway, goes into a forebay. This forebay will capture sediment. You really need to have a sediment. You need to capture sediment because then this will flow over into your infiltration basin. You don't want too much sediment get into infiltration basin because then it will clog and it will not infiltrate. So this should dry out within 72 hours. And this helps recharge your groundwater. It captures, you'll have pollutant removal using the infiltration basin. So over here on the right, this is an underground infiltration basin. So you'll have runoff from your parking lot. It'll flow into a catch basin and to a structure that will divert the water into the different bays for your infiltration. And there's usually gravel underneath. And it will store the stormwater, and they can be designed for large events such as 100. And one thing we always require on anybody permitting with us, if they're doing it underground, is to have a isolator road. Usually you also require them to have some kind of pre-treatment, a catch basin, maybe another structure such as a storm scepter in order to capture as much sediment, because as soon as sediment gets in there and you start losing your ability to infiltrate, it gets expensive to repair it. So we also have an isolator row that all the water going first, and that would capture whatever sediment makes it past your pre-treatment. And you have clean out ports, and you're able to then clean just that one, and you're not impacting your other bays there. So it's a very common way of infiltrating water. So you're recharging your groundwater, and it's a big component of stormwater management, is trying to infiltrate your water. But you also have to have, and there's a caveat with that, is you have to have the appropriate soils to be able to do that. So the next one, we're talking about constructed stormwater wetland basin. It's also known as a gravel wetland. So here you have, you know, the water comes in, goes in, you have wetland plants. They'll take up nutrients and pollutants and sediment. It will drain through into crushed stone, eventually drain from one. It'll travel through this cell into pipes into the next cell, gets additional treatment, and eventually be discharged out. So we actually have one in near our, as part of our stormwater system, our direct discharge system to take direct discharge from the roadways into the reservoir, Wachusett Reservoir. So and we'll go over that. Next, porous pavement. Now, this is designed so it's looks like regular pavement, but it's got a lot more. It's got a lot of voids or spaces within the pavement, and that allows water to infiltrate through the pavement, because typical pavement, it just runs off. It doesn't infiltrate. So this will allow the water to go through. There's different layers underneath, and some of those have a lot more void space. So it allows a storage of water, stormwater, and that will eventually infiltrate into the soil. But also they do have, sometimes they do have drain pipes in there in order to drain stormwater away. And then on the right, these are permeable pavers. So they're like brick or concrete, and they have gaps in them. So this one's sort of a green one where you'll fill the soil in between the pavers, and it will create, or the gaps in the pavers, and it allows water to infiltrate down. Sometimes they'll look just like regular pavers, but they're designed to have gaps, so the water will run in between them and then soak into the ground. Rain barrel, very simple. It's doesn't really look green when it's blue, but it captures and stores water, stormwater runoff. Comes in very handy when you aren't allowed to do any outside watering because you're in water restrictions, which my town was in this summer. I think it's still in. But you know, you can water your plants with it. It doesn't take a lot of rain to fill this. You know, a 1/4 inch rain with 10 foot of gutter in the downspout will fill a 55 gallon. You know, they'll range from 40 to 55 gallons, sometimes 60. And also, a lot of times, some towns will have programs where you can get rain barrels at cost, and a lot of that is done through, you know, cooperation with DEP. Next one is a cistern. Now, this is a much larger storage tank to capture water and store it. It can be used for irrigation. It can be used for fire suppression. I know there in the town south of me, they some of the neighbors, they don't have a water system. Everybody's on their own wells. They don't have a fire water system of hydrants where they can get water. So they have cisterns that stormwater from like a subdivision development will run off into these cisterns, and then they have a pipe where then they can pump the water out of it for fire purposes. So they can be quite useful. Capture the stormwater, and then you can use it later. This is where we'll, so this is one of the stormwater systems, part of our direct discharge program. This is on the other side of the causeway from the old stone church. So this is on the south side. This is in West Boylston on Route 12. So it's composed of 3 forebays. We have a detention basin, and then we had a constructed wetland basin or a gravel wetland. So you have your input. So right here, you can see going in the 4 bays, you have pipes that will bring the stormwater from the roadway and then put it into a 4 bay. So we're trying to capture these, the sediment. Then it's going to go from the 4 bays either into the detention basin or directly, if you look to the right side, directly into the constructed wetland. And then it will go from the detention, so it'll go into the detention basin, eventually from the detention basin into constructed wetland. And then after it makes its way through the constructed wetland, it will come discharge. So you see this spot down here at the lower left arrow, that's where it will discharge and then make it into the reservoir. So we start with a catch basin. Those catch basins right there. This is not, you want to make sure that they're not clogged so the water does get into them because you're trying to capture stormwater. It goes from here to the catch basin. It's a deep sump catch basin. So that will capture some sediment and then it will come into, this is your sediment 4 bay. It has an impervious bottom. Most sediment 4 bays do not have, they will drain, but because of the desire to prevent, if there was a spill along this roadway, that this would help capture any kind of oil or fuel that was spilled, and it wouldn't allow it to seep into the ground. And then we have this oil control structure that's designed to prevent any kind of fuel or oil that gets into a sediment 4 bay from going into the detention basin or the gravel wetland. And this is the detention basin. It's long. It's designed for a 100-year storm, so it will take a 100-year storm. At the far end, you'll see another oil control structure. So that will, the water will come from this 4 bay here, down this way, and then we'll go into your gravel wetland. So here's the gravel wetland here. This is the discharge pipe from the detention basin. This rock area here is an emergency spillway. So if the water gets too high, it will spill over. The reason you want to use like large stone, is to prevent any kind of erosion or cutting of the bank. So this would prevent that. And the water then will come into this gravel wetland and eventually it will soak down. The plant will take up the nutrients. So you have here in the lower right, you have these wetland plants. You see a lot of cattails. I don't want any kind of hardwood trees growing in there. You want to keep it more herbaceous vegetation. And then you have your leaching chambers here. If you went back to that diagram about the constructed wetland, this is very, very similar to that. And these change, so the water will come from the right, go to these. There are drainage pipes here that will take it, move it through. They'll collect it and move it through this berm here into this, and then it will release into the gravel and this cell here, eventually make its way to the discharge pipe at the far end and then into the reservoir. That's a pretty big area that has been used to capture stormwater to protect the reservoir. So now there's, another issue take up for Gray Green is wastewater. So we have composting toilets, household septic systems. I'd say that's more of a gray system. Alternate or enhanced septic system, probably classify it more of as a green system. Constructed wetland septic system, green. Community cluster septic system, classified as gray. Constructed wetland wastewater treatment plant. That would be considered a green infrastructure. Then you have the municipal and your regional wastewater treatment systems. And then last, reclaimed and reused wastewater. So composting toilet, you'll see these, you go to Mass Audubon, they have, they have some in some of their sanctuaries or facilities. Usually your waste goes in here. You've got to put in organic matter such as leaves. That'll decompose. You have a vent to take the smells away, and eventually you have to clean this out. But it works. Good thing about it, doesn't use any water. This is your conventional septic system, the household septic system. Your waste comes from the house, goes into a septic tank. Here, your solids will settle out, and then the fluid, which is a liquid, will go to a distribution box and then to what they call drain field. What we up here usually call it a leaching field. And so that's usually sand and gravel that allow the liquid to, it's all perforated pipe there, allows it to soak into the ground, where bacteria and stuff will eat away at the pathogens and anything in that liquid. And so the water will be cleaned as it goes down into the soil. It does recharge the groundwater. There are issues that if you see the groundwater well there, you have to, and dependent on, regulations, but groundwater has to be, the well has to be a certain amount of distance away from your leaching field. Also, there's a certain amount of space required for a leaching field, so that can also be a challenge with, putting the septic system in. There are issues with septic systems failing. They do have a limited life. There's also issues with soil. So if you don't have the adequate soils for it, then that can be an issue with using a household septic system. There's alternative or enhanced septic system. This is just one type. There's different ones. They're designed to treat the, use this one here as an aerobic. So it's injecting oxygen down into the tank, and it allows bacteria to more efficiently eat the sludge or the solids and clean the effluent, so then it will come up and then go to your leaching field. So you have those microorganisms is what you want. And you'll see that this is used actually in much larger treatment plants as one of the treatment methods. This is a wetland septic system. So this is where you're saying similar. It's just that it goes to a tank, you probably get some settling, that effluent then goes to a sort of a wetland cell where the plants will take up some of those nutrients and pathogens, and then it will soak down into gravel and then move to your leaching field. it's using microorganisms to be able to help treat that wastewater. One issue is that, may not be viable for northern climates, at least for now. Sorry. Next one. This is a community or cluster septic system. So this would be where people have their own septic tank. Actually, you could even just have one septic treatment or septic collection tank, and then it would go to a leaching field. And that's one way of using limited space, especially if you're using like a cluster development where you have houses are in smaller lots. You could preserve more open space by using a cluster type septic system. So this is something I found doing a search. It's a constructed wetland wastewater treatment facility. It's down in North Carolina. So what they do is it's designed to treat up to 500 gallons per day. Typically, it treats about 250 gallons per day. The treatment is, so wastewater comes in, they aerate it. So there's your aeration to get bacteria in there, eating away at the wastewater. And so it keeps moving along, comes in, keeps moving, keeps getting aeration. This allows additional treatment going through the serpentine system until it comes to a point where then it will be distributed into wetland cells. These wetland cells are where you're going to get that filtration, where they're going to take up a lot of the pathogens, the nutrients that you're trying to get rid of in your wastewater stream. Then they're going to disinfect it with chlorine, and then they dechlorinate it in order before they discharge it into a waterway. You do not want to discharge chlorinated water into a waterway because it will have a negative impact on the aquatic life. So this is a sort of a small municipal or a small regional wastewater treatment facility. This is in Westboro. So it treats wastewater for Shrewsbury, Westboro, and a little bit of Hopkinton. Treats about 5 to 6 million gallons a day. Treatment process. So they have a settling in your primary system. Then they use aeration. They have phosphorus removal, they have disinfection, and then they have dechlorination, because this will be discharged into the Aspet River. You see they've got solar panel that helps power the plant. So there is a green component here. Now this is MWRA Deer Island treatment plant. So this is the big one. It handles sewage from over 2 million people in 43 communities throughout the greater Boston area. The plant treats an average of 380 million gallons a day with a peak capacity of 1,200 million gallons per day. It's these eggs there are actually digesters. They help break down the sludge more. And in the process, they create methane. And that methane is actually used to help power the plant. So recycled, reclaimed wastewater. So when I was first started my master's program in environmental engineering, I did a report on reclaimed wastewater, and I found a place. So this is like probably about over 20 years ago, out in Irvine, California. So this is, they take wastewater and then they treat it. They'll use advanced waste treatment process that provides additional level of treatment. They store the water and then they'll use it for various purposes. One is irrigation. They'll use it for toilet flushing. So they have buildings, and because it's a city, they have a law that any new building built had to have a dual system where they had, so it had to have portable water, but it also had to have secondary use or reclaimed water. So the toilet flushing, the water for that is supplied by the reclaimed wastewater. And so they had a whole system to bring cross connections, and that's the pink. So those pipes are pink to identify them as reclaimed water. So they use them for also cooling towers for the commercial buildings, also for industrial processes such as concrete plant or any other type of process where they don't need pure potable water or drinking water. So it is clean water, but it's just not at the level of drinking water. So I know also they've used this type of water, reclaimed water, for injecting along the coastline into the ground as a way of preventing saltwater intrusion into the aquifers. So this is something that they've been doing for a very long time. I know down in, I think, Tampa area of Florida, they do use reclaimed water for irrigation. So this helps reduce the demand for or the requirement for drinking water, and reduce the quantity of drinking water that's required. So, talk about drinking water. So, what would it? So for green, I don't know if you want to call these green infrastructure, but a dug well, hand pumps, you have artesian wells, household wells, and then I've thrown in there forest and vegetated open space, and we'll talk about that later. Gray infrastructure for drinking water would be a municipal well and treatment plant, municipal reservoirs and treatment system, or regional reservoirs and treatment systems. So you have a dug well and you have a hand pump. It's like, well, how can they be green? Well, I'm going to put it to you that I think they would tend to conserve the water, because you're not going to use a lot of water if you're going to have to haul a bucket of water up to the house all the time. So you're going to use your water, conserve your water. Same thing with the hand pump. It takes a lot of effort to do that, haul it. Even if it is inside the building, it takes a lot of it. It's just not like turn on. So I'm going to say that more effort you have to put into the less likely you're going to use a lot of water. Artesian well. So an artesian well is where water will flow up from a confined aquifer. That's something that, and so it's saddled in between two confining layers, and it creates pressure that if you put a pipe into it and you're below the pressure level of that confining aquifer, you'd produce a flowing artesian well. And that would actually use a lot less energy than if you had to draw water up from a regular water table, such as you look on the right at the household well here. You need a pump to bring that water up into your house. So you need to use energy. So this is a typical household well. You would bring, you're going to have it drilled. You go into your water table, your aquifer, you put a pump down there. When you need water, it get pumped up into typically a pressure tank. So that will fill it up and it creates a reservoir. And that pressure tank would then provide the pressure you need to be able to send water to your faucets. So here we have a small municipal well and treatment system. This is Boylston Water District. So you have your well down here, and then you have your treatment here. It's a very small system. They have 5 gravel pack wells located in 3 different places. Serves about 70% of the town. The average daily demand is about 47,000 gallons per day. It's not a lot. But their treatment is only really pH adjustment and then disinfection. So it's a very simple system, doesn't use a lot of energy compared to a system where you had a lot more treatment. The system does, looking at a report, I think it was back in 2016, they had calculated that unaccounted water was about 6.7. So that's what they consider to be water that is lost within the system, either through leaks. Next we have this is a municipal well and water treatment plant, a little bigger. It's bigger. This is actually for my town, Ashland, and it also provides some water to Hopkinton. Has 5 gravel packed wells all in one location. So it's a sole source, which can be an issue. Serves about 87% of the town. Daily demand is about 1.325 million gallons a day. Treatment is they use aeration, flocculation, which is a method of injecting chemicals that help cause the sediment stuff to coagulate, and then they run that through a filtration system of sand and granular activated carbon. And then they'll disinfect it with chlorine, and then they will adjust the pH. So this is right next to Hopkinton Reservoir. One issue they have is that even though they're gravel packed wells, excuse me, they are hydraulically connected to the reservoir. And it does have an impact on the reservoir levels. And once the reservoir gets to a certain level, the town has been put on even greater water restrictions. So that's always an issue. And then one of the reports looked at was about 15.6% unaccounted water. So I tell you, they're losing water, and maybe because they just have a lot of pipes and stuff throughout the town that can have leaks. So this is the system that we're involved in at Wachusett. So this is a regional, it's almost statewide, but regional water supply, treatment, and storage system. This provides water to over 3 million people and 51 communities. Most of those are in the greater Boston area. There are some in a few towns and communities in Western Mass. Chicopee is one, South Hadley Fire District, and I forget the other one. You have in the central part of the state, they do provide water for some communities there. And also in sort of the Metro West area. Some of the service is full-time, some is partial, or some may be just as a backup. to their own regular system. So right now, I can tell you what Ashland, because of the drought and the drain on the reservoir, that we did emergency hookup to Southborough. And Southborough uses MWRA water. So I am now drinking Wachusett water. But the water then will go from Quabbin to Wachusett, then to Carroll Treatment Plant, water treatment plant in Marlborough, and then from there it goes to distribution system to Boston. They do produce hydroelectric power at 3 different locations. So they do provide some benefit in the transmission tunnels where they have turbines to create electric power. So this is Quabbin Watershed. So everybody thinks all the water comes from Quabbin, and quite a bit of it does. So its capacity is about 412 billion gallons. The surface area of the reservoir is over 24,000 acres. The total watershed area, that would be in the blue line, that is just under 120,000 acres. The land part is over 95,000 acres. Within the land watershed, about 93.6% is either forest or wetland. Of that area, the Division of Water Supply Protection controls 65% of the watershed, and another 20% is controlled by other agencies, state agencies, maybe local, and then non-governmental organizations, such as land trusts, Mass Audubon, trustees of reservation, organizations like that. Ware River Watershed. So Ware River Watershed, the Ware River provides water. It can either go to Wachusett or Quabbin. They'll take water out of Ware River. That can only occur between October 15th and June 15th. And it can only occur when the flows in the river are greater than 185 million gallons a day. So, and they can divert that water to, typically they divert it to Quabbin to help replenish Quabbin if need be. The watershed area is almost 62,000 acres, and that'd be this blue line here. So the light green that you saw, that's all these Division of Water Control, water supply controlled lands. So same thing, Quabbin, all that light green is DCR land. The land is forest to wetland is about 76%. And we control about 41% of the watershed, and other agencies and NGOs control another 17%. So we're talking almost 60%. In the Wachusett watershed, so we have a capacity of 65 billion gallons. Reservoir is, surface area is over 4,100 acres. Total watershed area is 74,800 acres. The watershed land area is just under 71,000 acres. The watershed lands, about 74.7% is forest or wetlands. And the DCR controls about 35% of the watershed, and other agencies and NGOs control about 21%. So a little over, so about 56% of the watershed is protected open space. So Wachusett, now everybody thinks all the water comes to Quabbin, but Wachusett typically supplies Boston from June to May. So in the winter months, because demand is lower and the inputs are usually higher from, storms, we tend to get more. Wetter season is during the fall and winter and into the spring. So we will supply Boston with their water during those months. So you can see also that we don't own a lot of land compared to, control a lot of the land compared to Ware River and particularly Quabbin. So that all goes so Quabbin flows into Wachusett, and then Wachusett flows to the Carroll Water Treatment Plant in Marlborough. So this treatment plant will service about 46 communities. Average daily demand is about 200 million gallons a day. Typically in the winter, you're down around 175, and during the summer, you can get up to 250 or higher. So maximum capacity is about 400 million gallons a day. They could treat, treatment, disinfection. They do disinfection by ozone, ultraviolet light, and chlorine. They also add fluoride, and they do pH adjustment. And you see this area right here? That's a solar array that produces about 500 kilowatts of electricity. So that helps, power the plant. So now, you're looking back at the, when I talked about forest and open space, the water quality at Quabbin is much better than the water quality at Wachusett. And that really has to do with the amount of protected, how much of the watershed is protected. Quabbin their watershed is much more protected. We control a lot more. So it really produces much better water quality. And that's really the factor that drives that is the amount of forest and vegetated open space. And that shows how, and that's why I sort of that called it as a green infrastructure, or you could call it a green system, but open space is important to good water quality. So we'll move on to flood control. So how do you deal with floods? Well, you can use flood walls, levees or dikes, which are earthen embankments, masonry or concrete dams, retarding floodwater dams, natural flood storage areas, and dunes. So you might consider the last three probably more in the green end of it as a green infrastructure. So flood wall, typically it's a, like a hardened concrete structure, or it could be steel or something like that, but it's designed just to keep floodwaters out from an area you don't want it. Levee or dike, this is usually an earthen embankment. It's designed to hold the water back. Same thing, keep the water where you don't want it, or keep it confined to where you want to keep it. Masonry dams. So these actually aren't typically used as flood control, but they have been occasionally. This is Framingham Reservoir 3, or also known as Foss. This is Sudbury Dam here on the right. They do will utilize them for flood control. If they know a big rainstorm, they may release water ahead of time. and create some, what they call freeboard, which means you allow for more storage than you normally would. And it gives you the ability to take up some extra flood water, and then they can release it later. So this is a flood retarding dam. This is actually Hop Brook here. This is in Northborough, and it's a natural resource conservation service dam. And it's managed by DCR, but the watershed area is about 3,145 acres. The normal pool area is 0 acres. And what we mean by that is there doesn't impound water normally. So there's no water behind it. The flood storage pool is about 146 acres. So that's the area that would be flooded if it was holding water back to its maximum ability. And the capacity would be about 429.5 million gallons. The NRCS has estimated that the annual flood damage reduction benefit from this dam is about $236,400 per year. So these look, like just an area with just a high area that would hold back water. This actually is near Northborough Crossing on Route 20. And there's a bunch of them, several throughout the Suwasco Basin, which is the Sudbury, Ascombit, and Concord Basin. So this is a natural flood storage area. So this is the Army Corps of Engineers back in the 70s realized that in order to help prevent flooding, that it would be good to use natural flood storage. And so they, in the 70s and mid 80s, they acquired 3,229 acres of land and 4,865 acres of easements in order to protect, so all this land and easements, this protects and provides and protects flood storage within the middle and upper Charles River. So this area here is actually, this is 128 right here. This is Cutler Park, and this is the Charles River right here. So this is a big wetland area, and what that wetland does is when you have a lot of floodwaters, wetlands are great. They suck up all the water. It's like a sponge, and and then they'll release that water slowly. So that helps reduce the amount of flooding you could get downstream. And so that's one thing, the Army Corps came to realization, they're known for building, dikes and levees and, dams. But this is something they realized was something that could benefit and reduce flood damage. And then dunes. So for the coastal, a lot of places are utilizing dunes. They're creating dunes and they're planting the beach grass in order to help prevent your storm surge from causing erosion or erosion from storms and causing damage, property loss. So dunes have one way of doing that. It's considered green infrastructure. Excuse me. We'll move on to climate change. So sea level rise, temperature rise. We'll go over changes in precipitation and storm intensity and frequency. So the relative mean sea level rise projection from now to 2050 for Boston is from 1.4 to 3.5 feet. And this is based on, this is based on the emissions. They modeled based on the different emissions and how much the temperature will rise. And by 2001, they expect it to rise anywhere between 4 to 10.2 feet. Woods Hole, similar, 1.3 to 3.1 feet for mid-century, and then 4.4 to 10.3 feet by the end of the century. In Nantucket, very similar numbers, 1.5 to 3.1 feet for mid-century and 4.2 to 10.5 feet by the end of the century. So projected temperature changes. So we have the first column here. You have the observed baseline from 1971 to 2000. And we have projected changes in the mid 2050s. So that's the range they sort of identified. And then projected changes in the 290s. So average net temperature is 47.6. They expect it to increase by 2.8 to 6.2 feet, and which would be a 6 to 13% increase. And by the end of the century, they expect an increase of 3.8 to 10.8 degrees, which would be an 8 to 23% increase. Maximum temperature is 58 degrees. They expect that to increase 2.6 to 6.1 mid-century. That'd be 4 to 11%, and then increase by 3.4 to 10.7 degrees by the end of the century. Minimum temperature, 37.1 degree is the baseline, and they expect that to increase by 3.2 to 6.4 degrees. And then by the end of the century, 4.1 to 10.9 degrees. And then days with maximum temperatures over 90. Currently, there's 5 annually. They expect that to increase by 7 to 26 days. So it's an additional. And that would be mid-century. And by the end of the century, they expect it to increase by 11 to 64 days. I don't know about you, but I don't think I'd like 64, additional 64 90-degree days. So why is minimum temperature increase important? Well, because that means we're going to have less snow and snow melt. And one thing for reservoirs is typically you get that snow melt, and that will help fill up the reservoirs. It also means that it will impact groundwater charge, because snow melt will slowly infiltrate into the ground and then recharge the groundwater table. If you have just rainstorms during the winter, particularly if the ground is somewhat frozen, that water will just run right off, and you're not going to get that groundwater charge that you would like. So snow can have a very big impact on groundwater recharge. All right, so for precipitation, this is the amount of precipitation. This is observed, so this is what they observed between 1958 and 2016. So this shows the amount of precipitation falling in the top 1% of all daily precipitation events. So that means that's the highest precipitation. So that'd be like a 100-year storm type of thing. The Northeast has shown an increase in the amount by 55% in the amount of precipitation. So that's what's already happening. So we see the projected changes. So baseline, so the same, similar information. So they got the baseline, mid-century, and then end of century. So total precipitation is 47 inches. They expect that to increase by 1 to 6 inches mid-century, and 1.2 to 7.3 inches by the end of the century. Days with precipitation over 1 inch right now is 7. They expect that to increase by 1 to 3 days, and then for mid, and then 1 to 4 by the end of the century. Days over 2 inch, days with over precipitation over 2 inches. Right now, it's 0.7 per annually. They expect that increase by 0 to 1 day for both mid and late century. And then a much bigger storm, which would be the 4 inch. Right now, it's 0.02 annually. And you'll see an increase of less than 1 per day for both mid and late century. And then consecutive dry days right now, we'll see 17. They expect that increase by 0 to 2 days mid, and 0 to 3 days in the end of the century. So when you're doing, as talked about when you file conservation under Wetlands Protection Act, you have to compensate for storm events in your stormwater systems. So typically we look at 2, 10, 25, and 100 year. So there's different ways of calculating that where you are. So federal government had what they call technical paper 40, and that was done back in 1961. They developed charts that would estimate what the rainfall for each particular event over a 24-hour period would be. So for 2 year, had a 3.1. So NOAA, so let me go next one. NOAA Atlas 14 is a sort of an updated modeling for what the precipitation is doing for those particular storm events. And then additional one would be the Northeast Regional Climate Center, and this is based out of Cornell. And they have modeling that they are estimating for these particular events. So for 2 year, TP40 is 3.1. That's the way it's been. That's what you're supposed to use for your stormwater events for calculating. And this is just for Worcester. It'll change for your different locale. NOAA Atlas 14, which is a more update, or more current. Both NOAA Atlas 14 and the Northeast Regional Climate Center are all current level calculations. So they have 3.12 and Northeast is 3.26. 10 year, you see 4.5. NOAA has it as 4.84 and Northeast as 4.92. So you see there's a little more of a difference between them. The 25 year, 5.3 for TP40. NOAA has as 5.92 and Northeast has 6.21. So you see that the difference between them is lengthening out a little bit as you get to a higher storm. And a 100-year storm is 6.5. For NOAA, that's gone up to 7.57. And Northeast has modeled it up to 8.87. And this is for inches. Sorry, I should put that in there. These are all in inches for precipitation event. So you can see how it's changed. And one issue is, you have these design storms, and under Wetlands Protection Act, we're supposed to be using TP40. They've sort of said, yeah, you can use NOAA 14 or maybe even Northeast, but they're not requiring you to use the more current models, unless you could, if you have your own wetland bylaw, you could require that under your wetland bylaw. And then what is in store for you? So projections, you're going to see sea levels will continue to rise. I mean, they've already risen. Hot days will become even hotter and more frequent. The overall climate will be warmer. So winters will be warmer, summers will be even hotter. Precipitation events will be more frequent and more intense. So you saw those storm events, how they're becoming you're getting a lot more precipitation in a 24-hour period than had happened in the past. So the impact, this will affect all infrastructure, both green and gray. Infrastructure built in the past cannot manage the storm events that they were designed for. So when you built a detention basin back in the 80s based on TP40, that would say be 6.5 inches to determine your calculation on the size of that basin. And now we're getting, if you use a Northeast model, you're getting over 8.8 inches. That basin may be not able to handle that storm event that it was intended to handle. There'll be greater stresses and demands on the infrastructure and the ecosystem. And this will be not just man-made, but also natural systems are going to suffer. Unfortunately, nature adapts, but they're not used to adapting so quickly to the changes in the climate. Usually it's a much slower process, and they'd have a lot more time to adapt to that. And they may not be able to adapt as well. So summary, you have the gray and green infrastructure can be identified for more than just stormwater. So we looked at different, you can do wastewater, drinking water, flood control. Green infrastructure works and can be an important tool in managing water. I would say if you can use green infrastructure, use it. I think it's much more aesthetically pleasing than a concrete structure or just a plain structure that really doesn't have any, visual value. Keeping water local is desired for protection of wetlands, rivers, and groundwater levels. So the more you can infiltrate locally, the better. Big sometimes can be better. So you look at Quabbin, Ware River, and Wachusett provide high quality drinking water to over 40% of the state population. And it also protects approximately 124, sorry, I made a mistake. I forgot the extra 1,000 acres of open space. The situation dictates the methods required, and usually combined approach is needed. So you can use gray and green, and all infrastructure needs to be maintained. Green just as much as gray. You need to make sure it's operating the way it's supposed to operate, and that means maintenance. And even though you can't just build it and forget it, which happens a lot, but there are ways of doing that. Our town has last couple of years instituted a stormwater fee, And so everybody gets charged a song, and this gives our DPW the money to be able to maintain the systems that have been built and maybe even improve them. So it's important to, get the funding to maintain these structures. Any questions? This is Wachusett at sunset.
It's a beautiful shot. Thank you. Thank you so much, Bill, for all of this. That's a lot.
We all leave.
No, there's still some people here. So folks, Kelly, do you wanna do this? Or do you want me to? I'm glad you're still here too.
You can do it if you like.
Okay, awesome. All right, we have a question from Richard. Can sediment from stormwater clog the voids present in porous pavement? Also,
Excellent question, and yes. And the way you maintain porous pavement is you have to vacuum it. I know it doesn't, they have machines, so you vacuum your porous pavement. One way is try to limit how much sand you put on during the winter. You still may get, stuff washing into it, but that's how you maintain porous pavement, is to vacuum it.
And can you tell the difference between porous and impermeable pavement as you drive over it or walk over it?
Yes, actually, you could go online and you can see that pictures where they have one half is regular pavement and the other's porous, and they dump water. And where it's porous, it just soaks right away. Where if you look in the regular pavement, asphalt pavement, it's just sort of shedding, and you can see how wet it is. I've been up to the New Hampshire, University of New Hampshire. They have a stormwater center there, and they do a lot of testing of these different stormwater structures, and they'll test to see how well they remove pollutants and maintaining. And they've done a porous pavement, and they showed us how well it worked, and it was really amazing. But it's expensive, and it requires, maintenance, a different type of maintenance than probably most everybody is used to having. Most people use street sweepers, and there's like a brush and a dryer, and it picks it up, and this has to be a different type of piece of equipment. But if more people use porous pavement, then probably the cost and the availability of that type of equipment will be a lot easier to get, or a lot cheaper to utilize.
Well, thank you. Catherine's asking, what will happen when or if the reservoirs run out of water?
All right. We're all going to go very thirsty. No, so actually Quabbin has basically, I think it's 5 years reserve, that even if we were in a drought, and for 5 years, it could still supply Boston with the water. Now, everybody else would be in tough shape, but I think it's something that people would have to learn to conserve very quickly. Daughters taking 1 hour showers would be a thing of the past. All right, maybe 45 minutes.
Okay. Thank you. Next question is, have you already seen deterioration of water-related infrastructure due to climate change?
I'm trying to think. Well, I think you can probably see it in some of the storm events we're getting, is that the structures aren't able to handle the flow that is being put into them. Pipes are getting overwhelmed. It's you can look at culverts that are built. This is getting away from stormwater, but culverts are failing because the amount of precipitation we're getting more intense storm events, and they're overwhelming culverts that typically in the past have been able to pass a storm. They're not. They're getting inundated, and they're getting washed away because of that. So that's I think the place you'll see it the greatest is in culverts. I think a lot of culverts are undersized for future storm events. Storm events are just becoming more intense.
Thank you. We certainly saw that out here in Western Mass with Irene. That 12 inches of rain in
I remember
12 hours was a lot.
Yeah, I went to a conference up in University of New Hampshire, and they had they talked about greatest storm events and everything, and some modeling. They actually did some modeling for Southwest New Hampshire, and I think it was in a year or two they had a really intense storm event that dumped like 11 inches of rain in an area. And it did exactly what they said. It overwhelmed the culverts and the systems, and it caused a lot of damage.
Cool. Let's see, Kelly, you had asked a question earlier, sort of, but I think Bill started to answer it. Is there, do you want to rephrase that or ask it the same way?
Sure. Bill, you said that stormwater BMPs are designed for a certain amount of rainfall under, I guess it would be Mass law or the standards. Would you recommend that these be designed for bigger storms at this point?
I mean, I think when you look at replacing a culvert, I think you have to model for a storm event in the future. Don't model now. Model for something in the future, or even you could even model it for now, but have them tack on, like we've sort of talked about it in if we revise our stormwater regulations, our bylaw, that we would require them to use like the Northeast calculations figures, and then tack on another, could be 10, 20% to that in order to be able to handle flows in the future. So, you're modeling for the future, but if you look at what's happened today, it's gone up anywhere, at least an inch or two for a 100-year storm in the past 60 years. And it's going to continue going up. So I would say a lot of towns can take that on themselves by if they have a wetland bylaw or stormwater bylaw. In fact, a lot of towns have to have that under the MS4 permits that are coming down from the EPA that they're required to have, and that would be like a component of it. Actually, it is a component of the MS4 permit is to have stormwater bylaw, and it's a good incentive to put one in. But as I said, you need money to maintain these. So, typically when a developer comes in and puts in a subdivision, generally they will, create a stormwater system, and then that system ends up going to the town along with a road. In most cases, not always. And now it's on the town to maintain it. And a lot of times towns don't have the budget. So being able to have a mechanism to maintain these is important.
Okay, and I have a second part to that question, Bill. If the Envirothon teams wanted to take this on as a project in their cities and towns and try to, I guess, convince officials that this is needed, is there a city department or person that they should start talking with?
Well, I think as far as it depends on what, if you're sticking to stormwater, it'd be DPW. I'm sure the DPW would say, I don't have the money to to sweep the streets, 4 times a year like they're supposed to, or to clean every single catch basin 4 times a year, or to cut the vegetation from all the stormwater basins that they have, or to, repair culverts that they have. And I think being able to, as I want to say, it's, a stormwater fee it helps. I don't know if there's another mechanism that could be put in place at a, more of a statewide level, like, we have under the CPA. The towns can get money for historic open space and affordable housing. And something like that could be a mechanism, so you have a dedicated funding, So when you're in the general budget and you're competing with everybody else, a lot of those type of things get pushed to the back burner. So I think talking to Concom would be very important, and the DPW, because the DPW can tell you what their problems are. Concom can probably help you figure out how to address it, or what issues they're seeing too. So Conservation Commission is a good place to start too. You may also have a Stormwater Advisory Committee or something like that. And that's a good place to start too.
Thank you.
Oh, I think there's another question. All right. Is the soil in Massachusetts usually adequate for septic systems and infiltration basins, or are amendments usually needed to make the soil adequate for filtration?
So with septic systems, there are a lot of regulations. They fall under the Board of Health, but there's also a state regulation, Title V, which is usually administered by the Board of Health, that you have to have a 2-foot separation between the bottom of your leaching field and your estimated high groundwater. The soils have to be appropriate. And I can't say that, Massachusetts, the soils in Massachusetts will be very different. So when you go down to the Cape, you have very sandy soils. They can, they drain very well, and you probably go to areas where you have clay soils, which won't provide the drainage you need. Infiltration. They do use different systems now where they'll use a raised system. So they'll create a mound and they raise it. But in those systems, typically you'll have to pump your effluent up into your leaching field. So that's an additional cost plus use of energy. Most septic systems use gravity, but it's I can't say that Massachusetts has great soil for some places probably do and other places don't.
Mm-hmm. Great, thank you. All right. Anybody else in our audience have one last question for Mr. Moulton before we wrap this up? Those are some excellent questions. Thank you all for contributing them. And I think we're good. So thank you so much, Mr. Moulton, for being here tonight with us. We really appreciate all this information, and I will get this posted to our website so that other teams can review it, and we can share this info with lots of teams. Thank you. Thank you, thank you, thank you.
No problem.
All right, have a great evening.
You too.
Bye, everybody.
Bye.